In the next hour, me and Hila, which I'm going to introduce in a sec, are going to talk about AutoML in recommender system. Okay, so let's start with the introduction. So my name is Assaf Klein. I'm managing one of the data science groups in Outbrain. And my colleague Hila is a data scientist and a guild master in the team. And today, we are going to take you through AutoML in recommender system. We'll start with the motivation for AutoML that you probably hear in the recent talks before me. And then we're going to give a quick crash course in recommender system. Our assumption is that you are not familiar with this domain. So we'll give a brief introduction, and then we'll go through a few interesting works in this area. And we'll also demo our own Outbrain AutoML platform in an interesting use case. And we're going to have some time for Q&A, and I'll also pause from time to time to ask if there is a question. So please write up, and then we can interactively do some Q&A. So let's get started. So why AutoML in general? So a very good property of a good machine learning production system is the ability to experiment a lot, to do very quick trial and error cycles, to try as many alternative model, pre-processing, a lot of experimentation. That is allow us to fail a lot, but on the other hand, to have a lot of success as well, and take our system forward in terms of model quality and our business KPI values. And if I'm trying to sketch, like to model it, how does it look like in industry or even in academics? So typically, we'll have a funnel of experiments, right? Wherein the top layer of this funnel, what is marked as 1 here, we typically will do offline research, okay? We're going to tackle and experiment with a lot of alternative, a lot of hypotheses, a lot of models. We like to test as many as possible options for solution to our business problem. We typically do it in offline, on an offline data, in an offline setting. We typically measure surrogate KPI, not the real business KPI. We like to keep it lightweight, fast, and of course, as automated as possible. And then the very few experiments that were success and was getting the best scores or the most successful, we'll take it to the next stage of the funnel, signed here as 2, the online research phase, in which we typically like to measure the business KPI on real data. In the internet arena, it's typically concerned with some kind of A/B test, okay? But again, we can have not finalized solution. It could be not that reliable, not that scalable, not that monitored, okay? And then the last stage is production, a bulletproof implementation, monitored, and so on, okay? So as you can guess, AutoML is typically done on the first phase of the funnel. And now that we have some kind of brief intro to why we need AutoML, let's understand what AutoML, how AutoML is applied in a recommender system. And let me give you a very quick course in recommender system, just to have an alignment with all the audience. So where do we find recommender system? What is a recommender system? So recommender system are all around us, in all the services that we are consuming online. For example, Netflix, Spotify, when we are reading articles in publisher websites. So in Netflix, you are opening your TV and you immediately see a bunch of recommendations for movies, from TV shows, which are personally tailored for your taste. Same goes for Spotify, right? You open the Spotify app and you see playlists that should hit your exact taste, your exact flavor in music. In Outbrain case, you are opening CNN or one of the publishers, the premium publishers in the world. You are consuming your news article or your piece of content, and then you see Outbrain content recommendations that are tailored for your taste, for your specific interests. Okay, and of course, in e-commerce, you are opening Amazon and you see all kind of product recommendation that you may or may not like. The key is that recommender system try to match users to items. So users, it's us. Items is depending on the domain, on the system. In Netflix, it's movies and TV shows. In Spotify, it's audio content, music, podcast. Outbrain tries to recommend great content for you, and so on and so forth. So how does recommender system work? Like very, very high level, and we'll immediately see where AutoML usually applied in recommender system. So it starts by the first stage, which is managing the available inventory. Okay, so in Netflix, you always have some kind of bunch of TV shows and active movies that you can watch. It could be thousands, hundreds of thousands, but usually this inventory tends to be very big, very large. And then in the next phase, you're going to filter this huge inventory to the eligible items. Okay, so for example, in the Outbrain case, if you are reading the Marker, the Israeli economic portal, so we probably will not recommend you with Japanese content, right? People like we will not even consider that. Or in Netflix, if you are an American, most likely a specific type of content will not be relevant to you. And then I think in phase 3, when we are left out with thousands of potential items, this is the most let's call it crucial part, where these items are being rated to suit your taste, or to suit whatever the recommender system is trying to optimize. Okay, and this is the rating function. And then the items are being rated, and only a few are being selected to be displayed. Right? If I need to recommend a specific user for items, for content links, then I'll rate everything and then select maybe the top 4. And AutoML is typically being applied in the rating function to craft the rating functions. And let's think what is a recommender system rating function. Okay. So typically it's depending on what the recommender is trying to optimize. So the most basic rating function is engagement, okay? In Outbrain use case, for example, a specific user is reading about a real estate deal in the Marker Israeli economic portal, okay? And I have maybe some information about the device, about different contextual features, and now I would like to aim for the most interesting or the most engaging items that I can recommend for this specific person. Okay, so typically engagement is being referred as a click-through rate. Okay, click-through rate, CTR in short, is the probability of this specific user to engage with my recommendation. Okay, so this is referred as CTR. Or maybe usually in the digital marketing industry, many times the target function is revenue or expected revenue. And this is a multiplication of the click-through rate, the probability of a click of a given user in a specific context, multiplied by the bid, by how much money I'm going to make out of this click. Okay, and there are more rating function that I can derive from the click-through rate, from the CTR, like maybe expected watch time in videos or expected long time value, maybe if I'm trying to recommend games or apps. But I think the main takeaway here is that estimating or predicting the click-through rate is a fundamental task in recommender systems. Okay, and this is actually what we are going to drill down, because in CTR prediction, most of the AutoML, at least works that I'm familiar with, is there. Questions so far? Okay, so let's do again a crash course in CTR prediction just to get the intuition, and I need you to understand the most significant challenge in doing CTR prediction or in modeling CTR prediction. And for that, let me introduce with a toy example from the ad marketing, from the digital marketing industry. Okay, so this is like a toy world, just to get the intuition. Let's say we have two publishers in our world: ESPN, which is a publisher for sport-related art news, and Vogue, which is for fashion-related news. Okay, two publishers only. And then we have two marketers. We have Nike, of course, selling shoes and sports goods, and we have Gucci, who sells fashion stuff. Okay, and let's say this is my data set. Okay, so let me explain for a sec. So in the first row, this is what happened when I listed Nike ads in ESPN publisher site. Okay, so I was showing 100 ads of Nike and ESPN and got 80 clicks. Okay, so my click-through rate was 80%. Okay, which is very nice. But when I listed Gucci ads on ESPN, okay, there's fashion stuff in sports, football readers, so I got very little engagement. I got only 10 clicks out of 100. So it's 10% click-through rate. So don't show Gucci and ESPN, but show Nike and ESPN. Okay, this is like the main takeaway. And if I look at the Vogue publisher listings, which is like the two bottom lines, you can see that Gucci did very well in Vogue, but Nike did pretty bad. Okay, so if I want to think of how to model CTR prediction, okay, I need to be aware of these interactions, right? Nike works well in ESPN, but works not that great in Vogue. Having this intuition in mind, let's take a look at like a very naive model, a very basic model for predicting click-through rate. Okay, so in general, what we have, how is the feature are being encoded is they are treated as categorical features. Namely, we'll have one category for publisher and one category for advertiser, and then we'll apply the simple one-hot encoding trick. Okay, so in the toy example I just introduced, we'll have two coordinates for publisher, two coordinates for advertiser, and for example, if I would like to predict how is Nike doing in ESPN, right? I will have 2 bits, 2 ones in the feature vector, and then I could train a logistic regression to learn a weight for each feature. Okay, so I will learn a weight for Nike, I will learn a weight for Gucci, I will learn a weight for ESPN, and I will learn a weight of Vogue, okay? Then I'll treat this logistic regression as a classification problem, train it in the usual methods that we all know, and I'll get a prediction model, a classification model that help me to assess the probability of a click given a context, given advertiser and publisher. Let's think together how this simple model will perform, okay? Bear in mind that this model needs to be aware of interaction. Nike work well at ESPN, but work pretty bad at Vogue. In this case, it will learn a weight per feature. So it will learn some kind of average, yielding a very bad model, okay? And now let me even sharpening this point, okay? So CTR prediction model are very sensitive to feature interaction. If you want to have CTR prediction model or a good recommender system in that sense, you have to have a very strong CTR prediction model, and you need to model feature interactions very well. Okay, so here another example, just to stress this point. So maybe in our example, ESPN readers like to click Nike, but don't like to click Vogue. So we probably need to add an interaction between publisher and advertiser. And maybe sports stories are being clicked more during morning time, because when you have your morning coffee, you are interested in how your team did in last night game. Okay, so maybe we need to add interaction of time of day and the ad category. Okay, and there are maybe less intuitive feature interactions. For example, maybe CNN readers that use mobile really like to read about diets, okay? And then you need to have this this third order interaction between the publisher, device, and ad category, okay? So so you can if you could you can suggest, okay, add feature interaction to logistic regression model, and all your problems are going to be solved. Okay, so we can introduce the Poly2 model that practically say, listen, take all the feature interaction you just add everything to your model. Okay, that's practically mean in our toy example, adding interaction between publisher and advertiser. So on top of the weights we learned previously for each individual feature, we learn a weight for each combination. Okay, so we learn a weight of combination of Gucci and Vogue, and we learn a weight for Gucci and ESPN, and Nike and ESPN, and so on and so forth. Okay, so let's say we learn this model. When we'll try to infer the probability, what we'll have, for example, in ESPN and Nike, we'll sum up the weight of ESPN with the weight of Nike, and then on top of it, we'll add a new weight of the interaction between Nike and ESPN, that in that case should boost our prediction and make it better. Okay, so are we out of problems? That's it? We have the perfect CTR prediction model? Not really, because if we'll zoom out a little bit, okay, and let's have a look on a more real-life scenario. It's not real life, but a little bit less toy example than previously. And let's say I don't have 2 publishers, but I have 5,000 publishers. And I don't have 1 advertiser, but 1,000 advertisers. And I have maybe 1,000 devices on 100 countries and 100 ad categories, okay? And this is not a real life example. In practice, cardinality is much larger, and the feature families are larger. We have much more feature families, okay? But even in this example, which is rather small, if I learn the Poly2 model as a whole with all the interactions, I'll come up with a logistic regression model with more than 12 million parameters, okay? And good luck with training this one, okay? Most likely, we'll end up with an overfitting model that is not doing that great. And there we go. We have the first AutoML opportunity in recommender system. Okay, so let's just do a quick recap. So we learned that feature interactions is a must when doing CTR prediction for having good recommender system, right? So you want to have good recommender system, you have to have CTR prediction. You want to have good CTR prediction, you have to model the feature interaction very well. But alas, if you learn all feature interaction, at least in logistic regression model, you probably end up with overfitting. So can we optimize this logistic regression model and select only the most necessary feature interaction, leaving out all the unnecessary feature interaction? Can we reformulate this question into a search problem where our search space composed of all the models, each models contain a different subset of feature interactions, and of course we would like to find the best model, the one that maximizes our accuracy KPI. Okay, of course this is rather large search space, hyper exponential. And now we can do a pause and let Hila, my colleague, to give you a flavor of how this can be resolved using AutoML, specifically with Outbrain AutoML we develop. So Hila, let me stop sharing. By the way, questions so far before we move on to the demo? Okay. Not everybody at once. Hila?
Okay, yeah, I'm here.
I think about the question, if people wish, they can do that in the chat and then you can just address it later, okay?
Okay, fantastic.
Okay, hi everyone. Can you see my screen?
Not yet. Yeah, we can see it, yeah.
Okay, cool. Okay, so I'm gonna do a quick demo of how we use AutoML in Outbrain. So let's say we continue on Assaf's example. So I'm a data scientist. I'm working on models for CTR prediction. So given a context, I want to accurately predict whether there will be a click or not. So as a data scientist, I want to do offline experiments. And for that, of course, I need the data. So the first component which we use in our AutoML framework is AutoML fetch, which basically downloads data, label data, and is divided to train and test. And during the AutoML fetch, we also do some pre-processing, etc. So for the purpose of the demo, I already downloaded some data. Let's just see the size. Okay, so we have around 2.2 million records. So it means we have the context features and the label, whether there was a click or not, and we have 2.2 million records of it. Okay, great. And it's divided to train and test. So let's say now I want to start searching for a model. So our AutoML framework is built solely in Python. So let's try to search. Okay, so we're searching. What are we searching on? So first we need to give the name of our folder where the data is. So this will basically be where we will train and test on many different variations. Next up, we need to save the intermediate results. This will help us, like Andreas said, to be shepherds of the AutoML, of the robot. We can the search is always saving the intermediate results, and we can either audit it, continue it, at different stages, etc. So let's just give it a temp there. Okay. Here we will save the intermediate results. And next up, we want to define what's our strategy in terms of what do we want to, how do we want to build the model? So we can say, okay, we want just add one feature at a time. We want find the feature interactions, the doubles Assaf mentioned, which is a big part of CTR prediction models, logistic regression based, of course. We can say do triples, do feature selection, hyperparameter optimization after we finish all these, etc. So for now, we just want the feature interactions, so it's going to be the doubles, and of course, we need some model to start with. So this can be either our production model if you want to test some new feature or we want to change the ML backbone. It can be if it's a new use case. It can be really basic, just a few features model, and then we'll develop it from there. So for the sake of this demo, let's say we have some basic model and we have 5 features which we want to test the feature interactions on. Okay, let's run the search. Sorry, let's give it a different temp there. This is something that I already ran. So let's just do it again so you'll see how quick it is. And just 1 second. So let's give it another temp there. Okay, now it's gonna run from scratch. Okay, yeah. Okay, so what's happening here? The first iteration, we have 11 instances. Why do we have 11? We have 1 for the basic and 10 for all the feature interactions possible. And we see that in each iteration, the component chooses the feature interaction which maximizes our metric. Our metric is RIG. It's a relative information gain. It's basically 1 minus log loss normalized. And at each iteration, we see that we start with the basic model, and each time we add the best feature interaction. Again, here on the second iteration, the best model was the one from the previous iteration, and adding feature interactions to that until we finished all the possible feature interactions. Okay, so just to give you a bit of an example what these feature interactions mean, so let's look at this, okay? To source from source, what does that mean? Okay, so Outbrain recommends content to users around the world, and let's say I'm a user that it's the end of the day and I just want to see some news about celebrities, and let's say I'm in CNN Entertainment. I choose some article about Elton John. I read it. I scroll down, let's say, and then I get to some article that looks interesting about some celebrity estate, and this is basically I get to another publisher. Okay, I get to Mansion Global, and it's about some celebrity villa. Okay, so basically what the AutoML found, it found a really intuitive feature that if I'm reading an article from CNN Entertainment, it makes sense to recommend something which leads to a celebrity section. So just to open up a bit the black box and see what's going on, let's look at this graph. It's a lot of animation, so I hope it will work. Okay, so let's say we start with this basic model, which is just, let's say, the site the user is reading. Okay, And then we want to test this feature with 4 possible other features about the ad, the topic, the URL, the image, and platform means what's the platform using to consume this content, mobile, desktop, etc. So each of these nodes, of course, is trained and tested on the same data, so it can be comparable. And also, of course, this is happening in parallel. Okay, this is very important for us. At Outbrain, we work with big data, lots of features. We want to be as fast as possible, and all of this is either trained on different CPUs, or we also have a flavor which is fully distributed, so implemented using Celery. And then it's like totally different machines, and you can 10x your speed. So each of these models is trained and tested independently, and the best, the model with the highest rig is chosen, and continuously until we get to the best one. Any questions I see on the chat?
We have some question in the chat, but we can save it to the Q&A.
To Q&A.
Yeah.
Okay.
Let's have 10 minutes at the end, Hila.
Okay.
Okay, your choice.
Okay. Okay. So yeah. So I showed you quite one of the use cases, but we use it really as that it's an amazing tool and helps us a lot for a lot of use cases within our group. It's not just for CTR optimization. Of course, I showed you the doubles options. We use it again for many different search configurations. And also we are focusing on logistic regression, but we also support more advanced algorithms for CTR prediction, whether it's field-aware factorization machine or deep neural networks, which Assaf will now talk about.
Thank you, Hila. Let me share my screen again. Okay. 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 So let's talk about some works that were published recently about AutoML in CTR prediction. I'm going to do, due to the time constraint, a shallow survey, but you can find the references and you can read it if you find it interesting. But let's start about what. So Hila did some kind of overview how to detect feature interactions in a search-based method. But one can imagine that wow, we have deep learning, and probably with deep learning we can model all the interaction we can by simply maybe, as you can see in the left chart, by taking the feature vector, the basic feature the vector, the one that we take all the categorical features and did one hot encoding, and simply apply some kind of fully connected architecture above it. Okay, one tower optimization. But unfortunately, this naive approach does not work. Okay, one of the reasons is this input feature vectors, the one that are in the bottom of this architecture, is with a lot of dimensions, a lot of coordinates, and it's very sparse. Okay, and when you're doing the multiplications, if you're like doing a fully connected, this becomes something that simply cannot converge. So there was a lot of research about how to model CTR prediction, specifically around the feature interactions in deep learning. And the general schema is as follows, okay? Generally, what these architectures look like is that the first layer is creating a dense representation for each feature, okay? Simply translate each feature from sparse to dense. This is the representation layers. Then there is above it, there is some kind of architectures that model the interactions between the features, okay? And after the interaction are being modeled, it is connected to, it is linked to a fully connected network that is doing the rest of the work till the final prediction is out. Okay, and like this is the general schema. There is a lot of methods, a lot of papers on how to model feature interactions. Like I'm not going to go into a lot of depth, but generally, if you are trying to map like works being done in AutoML for a recommender system and CTR prediction specifically, there is like three groups which I classified. The first one is something very similar to what Hila presented. It's simply methods to discover useful feature interactions. Okay, and this is like the first three. And then there is something more sophisticated that comes to say, okay, you have a deep model. Within this deep model, for each interaction, you have some kind of architecture modeling the specific schema of interaction in this specific feature. So why not searching for each feature a different, what is the best representation for this specific interaction? Okay, so this is kind of local model interaction search. And then you have, I think, more recent works around end-to-end learning. Okay, you are not bound to a specific model. Just give me your data, and I'll find what works best. So the first work is autocrossed, were published in KDD 19. It is kind of similar to what Hila just demonstrated. It's a distributed search engine in the model search space. It is doing a beam search. Each node is being evaluated using logistic regression, where in each, as the search progresses, a more feature interaction are being added. It is performing some kind of greedy search. And at least the paper suggests that on different data set, not CTR, it's kind of beat deep learning methods. But on CTR data set, the Criteo data set, it did pretty well, but not state of the art. This is something similar to what Hila just presented. And then this out-of-phase feature, which were presented at the last year KDD, is a two-phased approach. You first run some method in identifying most useful or best interaction, and then using this interaction, you extract from this method, you retrain your model, and you get better model because you left out a lot of unnecessary interactions. And this work specifically is inspired by Dart NAS that practically give a weight for each interaction, and then by applying some kind of gradient-based NAS, finds the best interactions. It practically worked very well on a CTR dataset, on Criteo and Avazu. It removes a lot of third-order interaction and a lot of second-order interaction, and it beat the state of the art at the time. So this is it. And there was some kind of generalization in out-of-phase. Out-of-phase proved to be useful on a second and third-order interaction, but it was not able to find any useful result with higher-order interactions. And then this paper, which kind of generalized out-of-phase, and I think it also get very good results on again, on Criteo and Avazu. So this is some kind of generalization and out-of-phase for higher order feature interactions. And there is also this very interesting feature paper, the out-of-features, which is kind of do search on the interaction architecture. So you have a specific model you chose to work with, and then this method come and try to find the best modeling, the best architecture within each individual interaction of a feature. And the premise is that for simple interaction, when the interaction is trivial, simple, then the architecture to model this interaction will be vice versa. When you have a complex interaction, it makes a more complex interaction structure in terms of architecture. Two methods that have a huge premise, which kind of say, listen, you don't oblige to use a specific model, just give me your data. This method have a few building blocks on how to model interactions, and then they have this search strategy in which they are trying to wire these building blocks to find the best architecture, the best model to fit your data. Specifically, AutoCTR by Facebook, presented in KDD 20, had the three type of basic interaction model, specifically this one, and then they have this search strategy. They try to combine them, and they show some very initial promising results on that. Another work is AutoRec, presented in RecSys 2020, which I think is like some kind of improvement over the previous, at least on what it offers. It offers much more expressiveness, meaning 7 type of building blocks to model interactions, and also built on top of TensorFlow and Keras, so you can actually take this model and do something with it. And they have very nice simple API. Haven't played with it yet, but it's looked very, very simple and cool. So there are more works. I kind of chose to select the most, the one that seems to get most traction. But there are more works in this map to one of these 3 groups. But to conclude, before we move to our Q&A, so generally, we give you some kind of very quick overview of AutoML in recommender system. Most of the use cases in a recommender system for AutoML is around crafting the rating models, specifically the CTR prediction, which is a fundamental task in recommender system. We also demonstrated how important is it to model well the feature interactions if you want to get decent model. And we mapped the methods into 3 categories in which we demo a live demo on Outbrain AutoML platform. And I hope you find it interesting. So we can move to our Q&A.
Fantastic. You have a lot of questions in the chat. You can do that as you wish.
Yeah, I roll up. Let's start from the beginning. Let's start. Okay, so we have Noam who asked, maybe I answered his question already, but he generally said, wow, why not using deep learning? Why use simple logistic regression? So yeah, we demo the logistic regression only because it's very easy to explain and to give the intuition. In practice, we are using more sophisticated models. I must admit that deep learning is hard to score in a recommender system, but we are not using the logistic regression in production currently. We use something better. Dvir asked why not to use all interactions. Again, if it's a question around why not use all interaction in logistic regression, I hope I made the point, because all the interaction mean to learn too many weights and you get overfitting. Dvir, maybe I got it. I hope I got it correctly. anyway. Andre asked how this tool can be configured, like which column should be processed and how. Hila, do you want to take it maybe?
Yeah, sure. So I guess you mean on the data, on the part of the AutoML fetch, you can configure which columns you want to use for your train and testing. Is that what you mean?
Mostly yes. You have a lot of different columns, different features of your data, and you may know that it may be possible, like adding this column to this column. Some subset of columns may be useful to add one to another, one to other. Sometime some columns may be multiplied, but you know that another column is date time, and there is no need to multiply somebody names feature column to date. How can we configure this?
Okay, yeah. So you're talking actually not on just pulling the data, but also that's in the instructions. Okay, we can say which feature. We can say, okay, we have no idea. We just used all the feature combination between everything, or you can say, I want to look at this feature set, try to add these feature combinations. So you can control it, yeah.
Yeah, maybe a bit more like what was demonstrated was a very, very simple TOA example, just searching some combination. In reality, the tool allows you to kind of instruct it either where to go deeper or what else to do. For example, feature transformation, binning, delinearization, etc. It basically can try, your usual use cases. You have introduced a new feature, and now you want to figure out how that new feature can best complement the existing model. And then you say, look, actually, just run 1,000 different ways how you can re-parameterize that feature and try to combine that with everything that exists. Or you want to do some hyperparameter optimization, and you say, look, do random search or something. But generally, the tool is there. You just instruct it, shepherd it where you want it to go.
Thank you.
Okay, we have question from double hyphen anonymous. Actually, if double hyphen willing to ask it verbally, I would be happy to, because I'm not really sure what the question is. I'll move to Ran Tavori question. How do you define the search operators, and how do you choose an evaluation function to the search stage? Hila, do you want to take it as well? I think it's on your part.
Okay. Okay, for the metric, yeah, it's configurable. You can say what's your metric of choice, and there was also an option to choose several, like rig and something else more based on ranking. You can play with that. And search operators, what do you mean exactly?
I can run po.
So yeah,
Run.
sorry. Hey guys. So yeah, I meant, how do you? I mean, from one search state, you need to move to the next X states, right? So you have a few options. For example, add another feature, maybe multiply a feature, and that. I mean, so how do you select them? How do you prioritize them? How do you define, the next set of states that you need to look for? You need to search for.
Okay, so you mean, okay, this is also flexible. You can say, I have several search strategies, let's say. I can say, okay, I want to exhaust, like adding all the feature interaction, and then try to do it in a higher order. Or you can do it in multiple, like at each state, choose the best one. Just do it completely greedy. Just add either feature combo or feature triple, if that's what you're talking about. So it can be either sequential or...
Okay, cool. Anyway, the first question was actually, how do you decide on the right metric, on the right evaluation function? I mean, how do you make sure that it actually provides you the best eventual result? I think sort of you maybe have answered that at the end of the session, though.
Okay. No, I can. Andreas, do you want to take it? I can take it.
No, Assaf, go ahead.
No, I mean, this is a very good question. Like, this is a subject to research. In general, we tried a bunch of function, and like we just keep working with what was aligned with like the business KPI we measure in production. So you probably can do better, I think, if you're willing to add, like, to do extensive research.
I guess it also depends on the use case, right? Because some use cases rig is better, and some are, you can think of something more ranking based, I guess.
Okay, got it. Thanks.
By the way, there are a bunch of questions about adding the links. So I think all the links I try to attach in the presentation. Uri is going to, I think, to publish the presentation so you can have a look.
Yeah, we will have the slides. In the slides, we will also have the links that you needed to add and also the recording. So don't worry, everyone. You will get everything tied together as you need.
Then we have Nisib. Is there a tool to implement feature interaction selection without neural network? Is that Nisib? Do you want maybe to elaborate, or I'm not sure I'm getting the question right? Okay, if Nissim will go live, so we let him ask the question. Dan Offer, you can run polynomial features with sklearn and then iteratively apply feature selection. Okay.
No, I think he answered Nissim.
Yeah, it was the answer from Nissim.
My bad.
He helped you out.
Oh, thank you, Dan. I appreciate that. For clarification, in deep reinforcement can be used to feature interaction selection. Maybe, I guess I'm not familiar with this type of methods. And this is the last question. Anyone else want to ask something that was not asked in the channel?
Regarding my previous question, I was referring to the demonstration earlier. It seems like it's adding features in an incremental fashion, similar to stepwise forward regression.
Okay, so it's more like a search, like what Hila demonstrates is more like a search engine that is like apply greedy search within a huge search space, guided, but so by some kind of heuristic, right? So maybe I'm not getting the question, but how it is related to what you ask, or you can maybe educate us about the stepwise.
Never mind, I think I get it. Thanks. Stepwise seems to work differently. Never mind, I won't go into the details today.
Okay, but feel free, like you can, we can have some kind of offline discussion. Feel free to ping us. Guys, any more questions?
While more questions pop up, I might just kind of give a bit more broader context. Like for those that listen to the keynote speech about the two AutoML kind of brands or two AutoML paths, like at Outbrain, we're in the path where really that less 0.01% squeeze really helps the business. And that's why we can invest so much into our tooling, into trying so many things. We have a couple of teams basically working on pursuing different directions, and one team working specifically on just improving AutoML tooling. Now, the interesting thing is, as Assaf was mentioning, that the general, deep learning approach from that we've seen in speech, NLP, or image processing doesn't directly apply. The use case is slightly different, but a lot of, with some modification, with some more work, of course, deep models can be used for this. However, they're extremely computationally expensive. And we're doing about 100 million predictions per second. Every second as we speak, 100 million predictions get made by these models. So we're trying to invest as much as possible to get the best intersection between CPU time and GPU time used versus the precision, because every precision point we get for the same hardware basically increases revenues. And that's why having such a machinery to do this offline really helps. And what was not obvious is like we do extreme batch processing. So usually for each generation, as we call it, we test like 1,000 or a couple thousand different options. What could be the best next thing to add, which interaction, how to weight the interaction, how to do the feature transformation or something like that. And we really kind of continuously run a machinery over all that. And I assume that not every company is in that situation. A lot of times, you know, the default algo will be good enough and you don't need to invest like 40 people all the time just to improve every last percentage point. So I would be, you know, a bit cautious about applying these learnings. If you have such a problem, if you really need to go as deep into this as the biggest companies are, yes, do your own. Figure out like on your own which metrics to use, everything. Otherwise, default tools are amazing. To use them. That would be my kind of final explanation. And if somebody is interested in more about what we do, we're always happy to talk. I think there are some very interesting things at this scale that become relevant that otherwise aren't that relevant in data science.
Perfect. You have one more question from Dvir. Do you want to take it?
Yes, so Dvir, running the search per day isn't too noisy. I mean, you probably need to run it several times to be sure, right? And then another question, are you testing online automatically? I mean, offline metrics does not have 100% correlation online. So I'll start with the second. Yeah, offline metrics does not correlate even 80% of the time. Yeah, we are also doing a lot of investment around automating the time from offline to online. Okay, so the whole MLOps thing is very strong. We are doing a lot of investment around that. And yes, the rig is not 100% correlated to what we see in online, definitely not. So you have to A/B test, and you have to A/B test a lot. Running search per day isn't too noisy. Well, I'm not sure what exactly Dvir asked, but usually we are looking at the offline data set are not a day size. I'm not sure if this is what he asked. We usually look at the larger than day data sets, if this is the question. That's it. By the way, I encourage you, we have Outbrain engineering blogs in Medium. We have a few posts around AutoML and about our algorithms that we are using in production. We have even open source, one of the mathematical engine we are using for a field-aware factorization machine. So I'll attach a link so you can read, and if you find this field interesting.